Hello, good afternoon, everyone. Let's wait for 1 more minute, sir, for the rest to come over, then we shall begin our lesson. Okay, so time switch for no man. So immediately we begin our lesson, shall we? So today we are going to continue from where we stopped last lesson. So in here, we shall do a little revisions before we continue. So last week we stopped at here where we have already learned how to about this ideal mixture of liquid. So in ideal mixture of liquid, to calculate the mole fraction, the vapor pressure, and the total pressure of the individual liquids exerted, so we use two laws. One is a Rock's law, another one is a Dalton's law. Okay, so in this we start from the steps 1, where we have Rock's law application. Where in Rock's law we use PA is equals to XA times PA naught. Okay, mole fraction of A multiplied by the pure vapor pressure of A. So this is step 1. And then after you calculate the PA and PB, so you shall go for the second step. So the second step is the application of Dalton's law, where you have PA plus PB in here. Okay. Then finally, after you get the P total, you are able to calculate how much is the mole fraction of the individual gas inside here by using the step 3. So the step 3 in here is the mole fraction of A and mole fraction of B in terms of gas. So XA gas is equals to PA over P naught. So this one you get from, this one is from number 1. Okay, and then this one is from number 2. Okay, so this is how you get the mole fraction of the vapor of A and B respectively. Okay, so we apply to the equation, then we are able to get this graph. Okay, as I already mentioned last week. So this is how you get the graph in here. That is why most of the vapor pressure, this graph is called as a vapor pressure composition graph. So in vapor pressure composition graph, so everything above the curve is liquid. Okay, and everything below the curve is gas. And what happens if the curve is in between here? So if it is in between here, okay, so this is where liquid and gas are at equilibrium. Okay, liquid and gas are at equilibrium. Okay, and then we have also already discussed what happens if it is under pure vapor pressure of A here. For example, at 130 kilopascal. So what is the composition in liquid state and also in gaseous state? So in here, there's 0.03 of A. Okay, 0.03 of A, 0.3 of A. That means you shall have a 0.7 B in here. Okay, so this is for gaseous composition. Okay, this is for gaseous composition. And then under the same vapor pressure, okay, you shall have the composition is in liquid. So the liquid form composition in here. So you shall have 0.4 of A and then 0.6 of B. So this is in liquid composition. Okay. So that is the way of how we are going to interpret this graph from here. So hopefully you'll be able to understand on how to get this curve. Okay. Okay, so that is where we stopped last week. So we are going to continue more on the examples of how to calculate the vapor pressure. So in example 1, given the vapor pressure of hexane and heptane are 10 kilopascal and 3 kilopascal respectively. If the mole fraction of hexane in liquid mixture of hexane and heptane is 0.40, calculate the mole fraction of heptane in vapor and that in the liquid mixture. Okay, so what is the mole fraction of heptane in vapor? So first of all, you have to calculate both mole fraction of heptane and hexane accordingly. So vapor pressure of the hexane is equals to XA times PA naught. This is pure vapor pressure of the hexane. Okay, whereas this is the pure vapor pressure of heptane. Okay, so you have, if you have 0.4, then the mole fraction of heptane is 0.6. So you get 4.0 and 1.8 kilopascal respectively. Then you get the total pressure. So total pressure will be 5.8 kilopascal. Then once you get this one, you're able to calculate the total pressure. So the total, then you calculate the mole fraction of heptane in vapor, because we want mole fraction of, if you look carefully at the question, we want mole fraction of heptane in vapor state. So you have PB over P total. So you have 1.8 divided by 5.8, you get 0.31 here. Okay, and then please, you also have to be very, you must also have the common sense. Why is it that hexane is 10 kilopascal while heptane is 3 kilopascal. In another word, why hexane vaporizes easier compared to heptane? So this one you must know on how to explain. Because hexane has a lower molecular mass or molecular size. So lower the molecular mass or molecular size, weaker the weak van der Waals forces. Okay, weaker the strength of weak van der Waals forces. So when you have weaker the strength of weak van der Waals forces, hexane is easier to vaporize compared to heptane. So that is why hexane has a higher vapor pressure compared to heptane. Okay, so this one you must know on how to explain. Okay, okay, so this is example 1. So immediately we goes to the second example, example 2. Mixing benzene with methylbenzene will give an ideal solution if the vapor pressure of benzene and methylbenzenes are 90 kilopascal and 78 kilopascal respectively. Calculate the mole fraction of benzene in vapor at the composition mixture of 2. One, if the mole fraction of benzene is 0.2. Another one is mole fraction of methylbenzene is 0.3. So how are you going to calculate this? So you have to calculate the vapor pressure of benzene and methylbenzene respectively. So for benzene is 0.20 times 90 kilopascal. For methylbenzene is 0.80 times 78 kilopascal. Press your calculator. PB is 18 kilopascal. Partial pressure of methylbenzene is 62.4 kilopascal. So you sum up, the total pressure will be 80.4 kilopascal. So you get the vapor. The mole fraction of benzene is equals to vapor pressure of benzene over total vapor pressure. So 18 divided by 80.4, you get 0.224. Okay. Whereas in mole fraction of methylbenzene is 0.35. So you expect the vapor pressure of the benzene here, if the mole fraction of the benzene is 0.35, so you expect the vapor pressure of the methylbenzene is 0.65. Okay, so you get the vapor pressure of benzene and methylbenzene are 58.5 and 27.3 respectively. So total pressure will be 85.8. So in vapor, mole fraction of the benzene, so 58.5 divided by 85, so you have 0.682. So with that, that is all for the things that you need to know for ideal mixture solutions. One of the things that you, if you notice throughout our discussion of the ideal mixture in here, you will notice one thing is, from this example, we can see this one is 0.2 is in liquid composition, isn't it? Okay, it's in liquid composition. So okay, So if this is the liquid composition of the benzene, you will see that vapor pressure composition is higher. Okay. Okay. If this is the liquid composition of the benzene, let's say this is a liquid composition of benzene, the gaseous composition of the benzene is this one. You see that when you mix between two ideal solutions, the one that we have a higher vapor pressure, so in here, methylbenzene is 90 kilopascal, methylbenzene is 78, isn't it? So the one with the higher vapor pressure, it will produce small vapor. When you produce small vapor, it is in a normal condition that the gaseous composition of the mole fraction will be greater than the liquid composition of mole fractions in here. Okay? Because once a substance is easier to vaporize, you expect that it has more vapor in the surrounding. And conversely, those with a lower vapor pressure is harder to vaporize. So when it is harder to vaporize, the gaseous composition mixture will be lesser than the liquid composition of the mixture. Okay, so this is something that you must know by yourself in here. Okay, this is number one. Number two, teacher, what are the mixture that can be called as an ideal mixture? Now, ideal mixture, as we have already go through previously, that it will have three postulates, isn't it? So what are the three postulates in here? The three postulates in here are like this. The last, the mixture in here. This is what we are talking about. Okay. Okay. So you have three postulates in here. The first postulate is intermolecular forces of A is equals to the intermolecular forces between B and is equals to the intermolecular forces of A and B. Of course, they cannot be exactly the same, but they are more or less the same. So what type of mixture will produce almost the same intermolecular forces? Number one, they shall have the same functioning group. This is more towards organic liquid. Most of the time, it's more towards organic liquid. So number one, they shall have the same homologous series. This is number one. Then, in order to have almost the same intermolecular forces, their molecular mass cannot be too great different. So if you notice from all the examples that we go through so far, hectane and hexane. Hexane has 6C, heptane has 7C. Benzene and methylbenzene. Benzene, for your information, also has 6C, while methylbenzene also has 7C. So you will expect that their molecular mass cannot be different too much. Okay, so with that mixture, it will form an ideal solution. If you want more example, another example will be ethanol and also propanol in here. Okay, another example is ethanol and propanol. Okay, ethanol and propanol. So they have the same functioning group alcohol, but their difference of the carbon is only one. So when ethanol mixed with propanol, then they will form ideal mixture. Okay, so that is how you tell when you form an ideal liquid, when we will not form an ideal liquid. Okay. Okay, so with that, that is all for ideal solutions. So we are going to continue the next one with what we so-called as fractional distillations. So now you have a mixture of liquid, ideal liquid, isn't it? So when you have a mixture of ideal liquid, how are you going to separate them? So this mixture of ideal liquid can be separated by using a technique called as fractional distillation. So fractional distillation is a technique used to separate between two miscible solutions. Okay, so the setup of the apparatus is shown as in this diagram. So you shall have a mixture of in between two ideal mixture liquid A and B respectively. Okay, then it will then, when you heat it, this is heating, so when you heat it strongly, okay, then the vapor will evaporate, isn't it? So when the vapor evaporated, okay, it will go to this fractional column. So this fractional column, if I zoom out, okay, it will look more or less like this one. This is the fractional column. When it zooms, it looks like this. It is made of the glass beads and all this and that. Okay, and then this is the condenser. Then after vaporize, okay, the vapor which has a higher vapor pressure will go through this condenser and then undergoes condensation to become liquid in here. So this is this will produce either your pure liquid of A or B in here lah. So this is the setup of apparatus of how to separate between the two liquids in here. Okay. So now, how do we eventually explain the principle of a fractional distillation? The principle goes like this. Those which have a higher vapor pressure, okay, those liquid with a higher vapor pressure, okay, or in another word, it has a lower boiling point, okay, so it will be able to vaporize easier, okay, you will be able to vaporize easier. So when it is able to vaporize easier, what will happen is the vapor that comes out here will be the one that have a higher vapor pressure, okay? And when it is vaporized, it goes through this condenser. Those with the pure liquid with the higher vapor pressure will be first produced in this case, okay? So what is the theory behind the usage of this fractional column in order to separate between the two liquids of, let's say, A and B in here? So we are going to find out together on how does the fractional distillation is applied. But before we go to how does this fractional distillation is applied, let's together understand another form of graph. So this form of graph will be boiling point composition curve. Now, this is a curve of vapor pressure composition curve that we deduced just now, isn't it? Okay, so where we have, this is the vapor pressure of the pure Px, okay, and then this is the vapor pressure of the pure Py. So you can see that Py has a higher vapor pressure, okay, Py has a higher vapor pressure. So when you have a higher vapor pressure, that means you have a lower boiling point, okay, that means it's easier to vaporize. Okay, it's easier to vaporize. So there's another form of graph that can be expressed by using this vapor pressure composition is boiling point composition curve. So how does boiling point composition curve is sketched? The boiling point composition curve is sketched. So imagine you're having a mirror in here. Okay. You imagine that we are like having a mirror. So this is the mirror. Okay, this is the mirror. Okay, you reflect the whole curve. Okay, you reflect the whole curve on here. Okay, you reflect the whole curve in here. So once it is reflected, so what will it become? Okay, so what will it become? Okay, so it will become something like this. Okay, so just now if you notice, this is the, when we said Y has a higher vapor pressure, okay, then you have a lower boiling point. Okay, you have a lower boiling point. Okay, higher vapor pressure, lower boiling point. So that is why you hear in here, you see the boiling point of pure Y is much lower compared to pure X, because in here X has a lower vapor pressure. So when you have a lower vapor pressure, you have a higher boiling point. Okay. Okay. So this is for boiling point of the Y, and this is the boiling point for the X. Okay. And in here, everything in below the curve are liquid, everything above the curve are gas. Okay, and what happened in between here? This is the equilibrium between liquid and gas. Okay, so everything within the curve lah is the equilibrium between liquid and also gas in here. Okay, so this curve, this graph is what we call as a boiling point. I erase this. Sorry. Okay, this curve is what we call as a boiling point composition curve. Okay, so this is a graph of boiling point composition graph in here. Okay. Okay, so this is the graph that we are talking about. Okay, so now we are going to make use this boiling point composition graph to explain the principle of the fractional distillation. Okay, are you ready? Okay, so now back to the diagram where we use this one. Okay, back to the point where we use back to the point where we use this graph. Okay, so just now we said that this is the setup of apparatus, isn't it? Okay. So in this diagram, you can see that okay, so this is the diagram used to explain the boiling point. Now, this is the heating mantle, isn't it? So this is where the heating source is occur. This is the heating source. So when the heating starts from here, okay, so the one that is the further away in here, in another word, in this fractional column, isn't it? In this fractional column, this is where it is the closest to the heating mantle, isn't it? So at here, this will be the place where you have a higher boiling point. Higher temperature, not higher boiling point, sorry. Higher temperature. As the column is further and further away from the heating sources, okay, this is where the temperature will keep on decreasing. Okay, temperature decrease. Okay, so in another words, here is where the temperature is lower. Here is where temperature is high. Okay. What is it? Yeah. So, okay, so we are going to explain here. Sorry. Okay, so now this is the place where we are going to explain fractional distillations. Okay, everything is inside the notes already, yeah. But here, what I'm about to explain is something once you are able to understand, then you'll be able to figure out lah, how does this fractional distillation principle works. Huh? Okay. Now, this diagram is the fractional column that I showed you just now. Okay, this is the diagram of the fractional column that I showed you just now. Okay, so this column has been reversed. The column has been reversed in here. The column has been reversed. So in another word, this is from top to the bottoms in here. Okay, this is from top to the bottom in here. Okay, where this is the place with a higher temperature. Where this is the place at a lower temperature. Okay, okay. So if you look at this is the boiling point curve. This boiling point is showing at a higher temperature, isn't it? Okay. So now, how does the principle of fractional distillation works in like this? Let's say now we have a mixture of composition of, let's say 0.2 of Y. So if you have 0.2 of Y, that means here you have 0.8 of X. Okay, so you start to heat. Okay, you start to heat. Okay, you start to heat from here. You heat, isn't it? So as heating occur, okay, as heating occur, some of the liquid will start to vaporize already, isn't it? So when the liquid start to vaporize, okay, what will happen under this temperature? Let's say we are heating now at this temperature T1. Okay, T1. Okay, T1, don't forget, is a higher temperature. Now we heated at T1. So when it is liquid is heated, liquid will vaporize to become gas, isn't it? Okay, it will vaporize to become gas here. However, during this heating of liquid to become gas, what has changes? You will notice that their composition has already changes. If you remember just now, we said that Y has a lower boiling point. That means it has a higher vapor pressure. You will notice that the mole fraction of Y is getting greater. Okay, Y is getting greater. So in another word, let's say if we have a Y heating up here. Okay. Okay, so Y is heating up here. So the vapor of the Y will come up together with the X, isn't it? Come up with the X. However, because Y has a higher vapor pressure, it is easier to vaporize. So in other words, you have more vapor Y in here. Okay, so as the temperature become lower, because it is further away from the mantle, so what happened? These particles collide with the wall of container, collide with the wall of the fractional column. So the one collide with the wall of the fractional column, what will happen is it will start to undergo condensation. Okay, it will start to undergo condensation. So when it collides with the wall of container, it loses energy. It undergoes condensation. So you shall have some particles Y, okay? However, less particles X in here. Okay? So that is why under this stage of the same liquid, same temperature, the gaseous composition of Y is now greater. So when it hits the wall of the container, it undergoes condensation. Okay, so during this composition, now you see it has a lower temperature already because why? the fractional column is further away from the heating mantle already, isn't it? When you are further away from the heating mantle, okay, so the temperature will become lower. Okay, temperature will become lower. Okay, so this is the composition at T2. Okay, so at T2, the process is keep on occurring. Where in here, the heating process is still keep on occurring. Some of the Y will keep on vaporize. Okay, so Y will keep on vaporize together with the X. X will also be vaporized. Okay, so the vapor will keep on vaporizing. Okay. Okay, so now at this second column, vapor X is going to increase greater and greater because vapor Y is going to become more and more as Y is easier to vaporize. So under this same temperature, so now Y has greater and greater composition, isn't it? Okay. So now has become greater already. Okay. So when it hit the wall of the container, okay, then it undergoes condensation again. So now it has become back liquid X and Y. Okay, but now Y has a greater composition. Okay, so this process of condensation, vaporization, condensation, vaporization, condensation, vaporization keep on occurring until the pure liquid Y is produced. Okay, because don't forget Y has a higher vapor pressure or a lower boiling point. That is why it is easier to eliminate from the mixture in here. Okay, so this is how the principle of the fractional distillation here works. Okay, now maybe if I explain like this, some of you still not very clear. So this one you have to rethink again and again. Okay, and then you keep on listening to again until you understand what am I trying to deliver in here. I'm so sorry this is the best I can talk to express to you how does this fractional distillation works. Okay, so teacher, is it really important in examination to explain? Now there is only 1 year in 2004 that asked about this process of fractional distillation. Then after that it never asked anymore. So in order to avoid you all not understand, hey teacher, how does this work? So inside this lesson I'll explain to you. Okay, so that is how the principle of fractional distillation works in here. Okay, so hopefully you all can slightly understand what am I trying to say in here. Okay, but if you still cannot understand, then never mind. Move on to the next one. Okay, okay, so that is how we explain the fractional distillation. Okay, so this is the explanation. So you can listen to it later on how we are going to explain. Okay, okay. So what are the factors that will influence fractional distillation? So there are two factors that will influence the fractional distillation. Number one is the distillation column must be very long. Okay, the distillation of a column must be filled with blast speed so that it will produce the larger surface area to condense and vaporize the liquid in here. And then number two is the length of the distillation column. So if the boiling point is closer between X and Y, let's say, if the boiling point of X and Y is closer, you require a longer tube in order to separate better between X and Y. Okay. So these are the two factors that will affect the distillation column used in here. Okay. Okay. So with that, that is all for the fractional distillation of an ideal solution. So I guess I'll stop my lesson for today. So because the last one, this one, the non-ideal behavior is more complicated. So if you can understand this, then our next lesson about this non-ideal mixture, you'll be able to understand better. Okay, so I think I'm going to end my lesson for today. So any question, you can always private message me. So if
Teacher, just now Mr. Lee call you, right?
Yeah.
He want to inform you about the e-sport helped by the what, I don't know, helped by someone. Then he asked us he